Hello and welcome to section 5.3, diagonalization. Today we're going to determine whether a given matrix is diagonalizable, and if so, compute the P and the D for this. So first of all, recall that whenever you raise a matrix to a power, that's the same thing as multiplying the matrix by itself, k times. So for example, a cubed is a times a times a. So if we let D be a diagonal matrix, then if we want to compute D squared, we write D twice and perform that multiplication. And so what we end up with when we do that in this particular case is we still get that 1 in that first diagonal, then we get a 4, and then we get a 9. Now for your quiz, you're asked to compute D cubed, which is D squared times another D, and so you're going to need this 1, 4, 9 diagonal matrix times your original D. And the question asks you what is in the lower right corner of the matrix you get. Okay, so if we extrapolate from that, when we raise D to the kth power, well, since it's a diagonal matrix, what ends up happening is we raise each of the diagonal entries to the kth power. And so this should match up with what you got in part B. So diagonal matrices are nice because, and a diagonal matrix is a matrix with zeros everywhere except the main diagonal. And those entries may or may not be 0. And diagonal matrices are nice not just because they're easy to raise to a power. Oops, let me just rewrite that. So they're easy to raise to a power and to multiply. We've already seen their eigenvalues lie along the main diagonal. So that's helpful. You can look at them and see their eigenvalues. And they're already in echelon form. So that makes questions about linear independence and span and that sort of thing easier to answer. So it's nice to be kind of close to a diagonal matrix. And so what we mean by that is if we have a matrix A and we can write it as P times D times P inverse, where D is diagonal and P is invertible, then our matrix A is said to be diagonalizable. And now we actually, first of all, we can use this to come up with a formula for A to the K when A is diagonalizable. And actually, you've already done this in your homework. If you think about it, we had a problem. Maybe the D I didn't explicitly say was a diagonal matrix. But here's the idea. When you multiply all these out, each of those, you get a bunch of P inverse P's, which become the identity multiplied by D's. In fact, there's K of them. So we have P, D to the K, P inverse. So that's one of the nice things with diagonal matrices. Diagonalizable matrices, sorry. Okay, so now we have a theorem called the diagonalization theorem. And this theorem gives you information about whether or not a matrix is in fact diagonalizable. So not every matrix can be written as P, D, P inverse. And so we need criteria to test that. And so in fact, it just needs to have n linearly independent eigenvectors. And in fact, the matrix P is exactly a collection for its columns. Each of its columns are linearly independent eigenvectors of A. And D is the eigenvalues. Okay, so A is diagonalizable if there's enough eigenvectors to form a basis for Rn, because if we have n linearly independent vectors in Rn, then we know that their span is also Rn, and so their span and linear independence makes a basis, and we actually call that the eigenvector basis. So let's go ahead and prove this theorem. So let's first, let's assume, well, actually, before we assume either way, let's just think about if we do have a matrix P, and so its columns are, we'll call them V1 and V through Vn, then if we multiply that by our matrix A, by the definition of matrix multiplication, we just take A times each of those columns, and that gives us the columns of our product. And then similarly, if we want to take P times a diagonal matrix D, and let's say D has lambda 1 through lambda n on its main diagonal, then, and so here's our D, so D has zeros everywhere else. Well, then if you think about what's happening when we multiply our matrix times our vector, the first situation is a vector lambda 1 with a bunch of zeros below it multiplied by our matrix, which is just going to pull out that V1 vector. And then our second column is going to pull out our V2 vector, and so on. And so we wind up just getting lambda 1 V1, lambda 2 V2, and so on as the columns of our PED matrix. Okay, so we're going to use that in a moment. So let's now go ahead and assume that A equals P, D, P inverse for some P. We can multiply P on both sides. So then we get AP equals P, D, P inverse P, and that becomes PD identity, which just becomes PD. So then we have AP equals PD, which implies, if we look up above, well, AP, we just calculated what that looks like. So here our columns are our AVI, and PD is our lambda I VI. So if we equate those columns, we have AV1 equals lambda 1 V1. AV2 equals lambda 2 V2, and so on and so forth, up through AVN equals lambda n Vn. And so these are our eigenvalues and eigenvectors. And since we know that P is invertible, well, that means that the V's are linearly independent. And so we have n linearly independent eigenvectors. And in fact, each of those lambda i's are our eigenvalues. So we've now shown that if A equals P, D, P inverse, then A has n linearly independent eigenvectors. Now let's go the other way. And so we are going to assume the hypothesis that A has, so this statement is an if and only if, right? So we're starting now with the A has n linearly independent eigenvectors, and we're showing that A is diagonalizable. So let's go ahead and give them names. Let's conveniently name them V1 through Vn. And then let's set P to be the matrix given by those. And let's set D to be the matrix containing the corresponding eigenvalues. Well, then P is invertible since the eigenvectors that are its columns are linearly independent. Okay, and so since the VI's are eigenvectors, then we have this equation. So then we can go back and kind of undo the work we did up above, that tells us that AP equals PD. So A equals PDP inverse by multiplying on both sides. So the main reason I went through this proof is not so much that I would expect you to reconstruct it, but rather that it gives us a chance to really internalize that theorem. Okay, so now that we know a matrix is diagonalizable, or if we know a matrix is diagonalizable, then we need to find a way to actually write it as our PDP inverse. And the basic idea is we need to find the eigen values and eigenvectors. And so in this case, I went ahead and gave you the eigenvalues. They're just 1, 2, 3. And now we need to find the 3 linearly independent eigenvectors. And so we can do this with each of our eigenvalues. So our first eigenvalue, lambda equals 1. Well, when we write down our matrix, and what I did is I subtracted 1 from that main diagonal. And so that's how we got everything else stays the same. We row reduce it to get 1, 0, negative 1, and so on. And so V1 is going to be 1, 1, 1. And so that's one of our eigen vectors. When lambda equals 2, again, we subtract, this time we subtract 2 from our main diagonal. So we get negative 1 minus 2 is negative 3. And then negative 3, 2, 0, negative 3, 1, 1. And again, we row reduce it. And in case I did that first one a little fast, let's remind ourselves this says that x1 minus 2/3 x3 equals 0. x2 minus x3 equals 0, and x3 is free. And so we have x1 equals 2/3 x3. And in fact, let's go ahead and write our vector. X is 2/3 x3, and since x3 is free, it's itself. And so kind of the idea here is that an eigenvectors here are multiples of 2/3 1, 1. And by the way, since they're multiples of that vector, any multiple would work, including times 3. So if we multiply that vector times 3, we get 2, 3, 3 is an eigenvector for A here, lambda equals 2. And then finally, we do the same thing for lambda equals 3, and maybe to save time on the worksheet, I'll go ahead and write down what you get, and you should go back and test this and make sure you get the same thing. It's the same process that we did for those, or any multiple of that. So I'm going to go ahead and multiply this by 4. So just in case you're not clear, I multiplied that times 4 to get there. To get a different eigenvector. I didn't need to do that. I just like my P matrix then to have whole numbers in it. So now I just take the 3 eigenvectors that I found, and those are the columns of P. So we have our first one, our second one, and our third one. And as long as these are linearly independent, then P is invertible. And we saw in a previous chapter that if they're distinct, then they're linearly independent. So we already know that these 3 vectors are linearly independent. And then D is our diagonal matrix where we put our eigenvalues in, and we just need to make sure that our eigenvalues match their corresponding eigenvector. And so in this case, our first eigenvector corresponded to lambda equals 1. Our second one corresponded to lambda equals 2. And our third one corresponded to lambda equals 3. So we have to put our D in the same order. And you can check this. You can do compute P inverse and do PD P inverse, and you should get A. Okay. Now we have one more theorem. So maybe we have a couple more, but I think this is the last one that we're going to go through a detailed proof on, I think. So if we have distinct eigenvalues, then our matrix is diagonalizable. Well, in fact, if V1 through Vn are eigenvectors corresponding to distinct eigenvalues, well, then in section 5.1, theorem 2, we have a theorem that says that V1 through Vn are linearly independent. And so that means that by that theorem up above, in your book, this is theorem 5. So by this theorem 5, A is diagonalizable because we just need n distinct eigenvectors. Okay, so for number 6, it asks us if A is diagonalizable, and A is lower triangular, and so in fact its eigenvalues are on the diagonal, and so we have 4, 3, and 5 are the eigenvalues, and they're distinct, so A is in fact diagonalizable. And then for your quiz, I'm asking you whether we have enough information at this point to determine if our matrix is diagonalizable. Okay, we do have one more theorem, but I'm not going to go over the proof of it. We're just going to talk it through. So we have an n by n matrix who has distinct eigenvalues, lambda 1 through lambda p. So that doesn't, notice that A is n by n, and we have p distinct eigenvalues. So what this means is there might be repeats. If p is less than n, we might have an eigenvalue that repeats more than once. And so the first thing the theorem says is that the dimension of the eigenspace is less than or equal to the multiplicity of the eigenvalue. And remember that multiplicity is the number of times it appears in the characteristic equation. Then we also say that A is diagonalizable if and only if the sum of the dimensions of the eigenspaces equals n. This is really related to that theorem that says A is diagonalizable if and only if it has n linearly independent eigenvectors, because essentially what's happening is if the dimensions are big enough, so if what's happening is, here's the key. If the dimension of the eigenspace equals the multiplicity of lambda k, then within our eigenspace we have the number of basis vectors is equal to the multiplicity of that eigenvalue. And so those are linearly independent. And then when you compare a vector from a different eigenspace, so from a different eigenvalue, they're also linearly independent. So you wind up with n linearly independent eigenvectors. And then finally, if A is diagonalizable and beta is a basis for the eigenspace corresponding to lambda k for each k, so each of these is a basis, then actually those bases put together form an eigenvector basis. Okay, so that's kind of a lot to digest, but let's look and see if we can use it to understand what's going on here. So we're asked if A is diagonalizable, and we have our 4 eigenvalues. So we have lambda equals 5, multiplicity 1, lambda equal, and maybe I'll make room here, lambda equals 3 also has multiplicity 1, and lambda equals 2, which actually has multiplicity 2. So up to this point, we don't yet know if our matrix is diagonalizable because of that multiplicity 2 thing. So if all of our eigenvalues had multiplicity 1, we had n distinct eigenvalues, and we know that their eigenvectors are linearly independent. But we could have a situation where we had a multiplicity 2 eigenvalue, but we only got one eigenvector in a basis. So the dimension of the eigenspace might be smaller. So let's just see what happens in this particular situation. So in lambda equals 2, we have our matrix A minus 2 times I. And then, sorry if you hear basketball cheering in the background. My family's very into the NCAA basketball tournament. And we have, so if you look at this carefully, this, actually I'm just going to go ahead, this becomes 3 and that becomes 1. And those are our pivots. And we have 2 free variables. That means we have 2 different vectors in the basis for the eigenspace of A corresponding to 2. And that means that we get 1 here, and 2 here. So we have 4 linearly independent eigenvectors. So our matrix A is diagonalizable. And a good test on your knowledge of your understanding of diagonalizability is if you can come up with your matrix P, your matrix D for diagonalizability. Oh, and one other thing I should mention, whenever you're asked to diagonalize, if you just write P and D, that's usually okay. You don't have to write P inverse. Sometimes it's hard to compute that inverse.